As we go through the life cycle of stars, let's start with where our sun is today. Our star is a middle-aged star, right smack dab in the middle of its life cycle. It is a white star, and as we've talked about in the past, it looks yellow when it is on the horizon because of the fact that a lot of the blue wavelengths are being filtered out by our sky. But our star is very, very stable. And if it was not stable, life could not have evolved on planet Earth. So we are very fortunate and grateful to have a stable nuclear furnace in our sun. What's going on in our sun today? It's busily fusing hydrogen plus hydrogen to make helium. We suspect it's been burning about 4.5, 4.6 billion years, and we think it has enough fuel for about another 5 billion years before it goes into the next stage of life. So it's smack dab in the middle of its life expectancy, and not something we should worry about anytime soon is going to be what's going to happen to our sun next. But we are creative and curious humans, so what is going to happen to our sun next? Well, in order to explain that, we have to closely examine what's holding our sun up as a star. There are two opposing forces. Gravity. Gravity, of course, rules astronomy. Gravity is caused by the mass of the sun, and gravity is pulling that star into a tight little round ball. Outward, there's also heat and pressure. There is a massive nuclear fusion furnace in the center of the star. It is producing huge quantities of heat, and that heat is blowing the star up like a big hot air balloon. Currently, those two forces are balanced. You've got a balanced set of forces here, and that balanced set of forces is referred to as hydrostatic equilibrium. Equilibrium meaning things are balanced, static meaning not moving. Hydro has anything to do with fluids, and the plasma in our star is actually a fluid. So you need to know this word, hydrostatic equilibrium. That's what's going on in any stable star. Now, what was going to become of our sun? The way we figure it out is again in that concept of a life in a day. If we look at other stars along the main sequence on the Hertzsprung-Russell diagram, we can see stars that are a little bit older, a little bit younger, and we can get a good idea about what's going to happen to our star next. Right now, our star is busily fusing hydrogen plus hydrogen to turn into helium. And that's what's giving us our stable star. But every fuel source is eventually going to run out. Eventually, when our star runs out of hydrogen to burn, or the hydrogen concentration gets low enough so it can't burn well, our sun is going to go into the next stage of life, and the next stage of life is referred to as red giant. So here's how this works. If you remember when we talked about that diagram of energy per nucleon, when you burn hydrogen and fuse those two together to get helium, you have a tremendously efficient energy source. Lots of power is produced per nuclear reaction. Well, eventually what happens as the hydrogen gets used up is it then starts to end up having to burn the helium in its core. So there is a partial collapse. There's not enough heat to keep the whole envelope blown up, and the interior core is going to collapse a little bit. What that's going to do is increase the pressure. The pressure in the core is going to go up, and when that pressure in the core goes up, then the star can start burning helium. Heliums can then fuse together to produce other things like carbon and oxygen. Now, to go up to carbon and oxygen, this is a less efficient heat source. It's kind of like, I don't know, burning pine as opposed to burning coal or something that is just not going to give you the heat per unit volume of whatever fuel you're burning. Because of that, the star is going to get cooler. And as you know, cooler stars have a tendency to be redder. So this star itself goes from being a white color or a yellowy white color to being redder, meaning it is cooled off. The other thing that occurs is the core in here does have a little bit of hydrogen left. And the little hydrogen that does burn gives off enough heat to make this whole big envelope of gas, that is our star, expand. And when our star goes from being a regular middle-aged star, as it starts to die and turns into a red giant, what it's going to do is it's going to get cool, it's going to get big, and it's going to expand. So the helium core, as that hydrogen starts to burn and fuse a little bit, that last little bits of hydrogen, you end up with this big, huge, expanded, cool envelope of gas, and that is going to be our red giant star. Now, how big is our star going to be when it ends up to be a red giant? Kind of depends upon the source you're reading. So I'm going to go with our textbook. Our textbook says that it's going to expand to about 1/3 of the Earth's orbit. So that's really big. This is an attempt at a scale picture. If this is the size of the sun now, it's going to get crazy nutty big. Poor little planet Mercury is going to be totally burnt up as the star goes red giant. And some reports, some scientists actually estimate that when our star goes red giant, it will get bigger than even that. Students ask me all the time, so when the sun goes red giant, what's going to happen to the Earth? Well, there's going to be a star that's going to be a lot closer to the Earth, but it is a cooler star. So exactly what's going to happen to the Earth, some estimates is that the Earth is going to burn up like a crackly little crunchy crisp. And some estimates say that the Earth is not going to change that much because of the fact that the gravity's not going to change, but the heat source will change. How long is this whole process going to take? And I suppose I should say this. The sun is going to go red giant in about another 5 billion years. So as I mentioned, don't lose sleep over it. It's going to be a long time before this happens, but that's going to occur when we start running out of hydrogen fuel. Now, back to that little diagram of energy per nucleon. If you start out burning hydrogen to make helium, you end up with a very efficient fuel source. You start fusing helium to get things like carbon and oxygen, less efficient fuel source. The star is going to change fuel every few years. And when I say few years, we could be talking about 100,000 years, sometimes 10,000 years, and sometimes as much as 1,000,000 years. But whenever the star runs out of one source of fuel, it is going to go through a weird collection of changes. So we're going to start with our sun on the main sequence. It will eventually expand and cool and turn into a red giant. And this is, of course, a Hertzsprung-Russell diagram. And that's where we think these giant stars come from. Well, periodically, whoops, I drew the wrong arrow. Okay, how about going this way? There we go, because that's the cloud of gas, the nebula that created it. Let's go back this way. When it starts running out of hydrogen, it'll expand into a red giant. And then as it switches from hydrogen fuel to helium fuel, it's going to compress a little bit. The star is actually going to get a little bit smaller. Pressures are going to go up, and then it will start burning the next fuel source, helium. When that happens, the star is going to expand again. It's going to burn for a while, use up its fuel. When that fuel is exhausted, it will contract again. When it contracts, the pressure goes up. Pressure means that it's going to start burning a different fuel, and when that new fuel gets added, the star will expand again. So it's going to go through this multiple shifts of fuel through time, and that's why on this Hertzsprung-Russell diagram, there's this kind of a sawtooth area of the diagram if you look at a star like our sun. Every time that fuel switch occurs, the star has a tendency to produce something that is called a planetary nebula. Now, the word planetary nebula, the name planetary nebula, is confusing. And these things were named long before we really understood nuclear fusion or before we understood the life cycle of stars. And so these nebula basically have nothing to do with planets, but the name has stuck, and so we still call them that. Here's what happens. every time the star goes through that switcheroo from one fuel to another fuel, it is going to, when it collapses down, it ejects some slow solar wind, a big puff of slow solar wind. With that collapse, what it basically, that slow solar wind comes from, if you've got a big star and it collapses downward, it's going to leave an outer layer of itself out there, and that's going to be ejected out into the solar system, and that is that slow solar wind. When the new fuel ignites, it's going to go poof, and you're going to have this new fuel that is going to ignite. And when that occurs, there's going to be kind of a little explosion. It's not as big an explosion like a nova, but it is going to throw out a big cloud of gas. And that is a fast solar wind. A star in the process of dying is going to do this over and over and over again. And each time it goes through one of these fuel changes, it puffs out these layers of gas. And they are beautiful to see through a telescope. And these pictures here are Planetary Nebula. And Planetary Nebula is the name given to these gas clouds that are emitted as a star switches fuel through its life cycle. Planetary nebula typically have a lot of green in them. And green, when you start looking at the spectra of elements, if there's a lot of green, that means there is a lot of oxygen and to some extent also a lot of nitrogen. Oxygen and nitrogen gives us these reds and greens and the same sort of colors that we see in the auroras on planet Earth. Now, after this cloud has gone through all of these different switcheroos into fuel, eventually, and I think I mentioned the last slide, it's going to blow off about 20% of its mass in one of these combinations of planetary nebula, all these gas clouds that it throws out sideways. What's left is a retired star. And those retired stars that are left over after a star has gone red giant are called white dwarfs. And those white dwarfs are cool and white and quite small. And we're going to talk about those in the next video. See you then.